Hello, my name is Yuri Zelenko, and I will be talking about the Senior Design Project, which is sponsored by the National Oceanic and Atmospheric Administration, also known as NOAA. The topic of the project is the design to improve the productivity and execution of gravity surveys. First of all, what is a gravity survey? A gravity survey is a collection of measurements of the acceleration of gravity. The data is used to model the Earth's geoid, which is used to map the elevation around the globe. The significance of this data includes floodplain mapping, detecting natural resources, and several others. It is estimated that the potential economic benefit of surveying the United States areas is around $4.8 billion. Executing airborne gravity surveys is a complex procedure. First, NOAA decides on the area where the gravity measurements need to be made. Once a location is selected, then an appropriate aircraft is chosen and flown to the most convenient airport near the survey area. The transit process will take 3 days on average, and the airport will become the base of operations until the survey is complete. After all the personnel and equipment have been transferred to the base airport, then the crew prepares the airplane. The measuring equipment is installed onto the aircraft and calibrated with test flights. An average flight block is usually 400 by 500 kilometers. The aircraft flies in a grid-like pattern, with the first flights being very tight-knit, where each flight path is 10 kilometers apart. After that, the airplane flies perpendicular lines 80 kilometers apart to verify the measurements. Once the whole block is complete, the equipment is uninstalled and all resources are recalled. Currently, NOAA has been accomplishing about 5.6% of the area covered annually. If the current trend continues, they will finish by the year 2026. NOAA will need to increase output to 8% in order to reach their completion goal by year 2022. To assist with this issue, we will first look at the historical data. The table is broken down by individual surveys in the columns and the particular process or delay in the rows. Each number represents the amount of days that each survey spent performing a particular task or waiting due to delay. The important factors that we will focus on are the aircraft maintenance, aircraft repair, equipment repair, weather delay, and personnel days. Using the data from the previous table, we derive the distributions for the major factors. This data shows that there is a lot of variability in these factors, which causes increased delays. The problem of this project is that NOAA is unable to reach their target completion goal with the current process and resources. They need to reach 8% area coverage while staying within budget. There is a need to improve the execution of gravity surveys so that NOAA may reach their goal. We will be looking mainly at two alternatives, with the third one being a combination of the first two. The first alternative is to focus on improving the logistics process. By determining which factors cause the most delays, NOAA can use mitigation strategies to avoid unnecessary downtime. The second alternative is to acquire additional resources such as aircraft, equipment suites, and personnel. Additional resources will allow for more surveys to be completed annually, but at an extra cost. The third is a combination of the first two, but this will yield the best result but may cost too much to be feasible. To analyze which variables have the biggest impact on the delays, the distributions were derived from the historical data as mentioned before, and input into the simulation. From the simulation, we could estimate the survey time and the relationship between the variance and delay reduction. The simulation was created in ARENA. Each block represents a process in the logistics procedure. The simulation begins at the Deploy Resources block, where an entity is generated. As the entity goes through each block, days are added based on static values or the calculated distributions. The simulation is run for 10,000 replications, after which the data is averaged and verified by comparing to the historical data. For the design of experiment, we reduce the variance of the major factors from 5 to 25% in increments of 5%, and run the simulation again for 10,000 replications. Then 10, 50, and 90% confidence intervals of the time to completion are calculated. Finally, to find the variables with the biggest impact, we subtract the new values from the original simulation values. The result difference was plotted, and from this graph we can see that the aircraft maintenance had the biggest impact, followed by equipment repair, then aircraft repair, then personnel day, and finally weather delay. The parameters were ranked by their impact, and we provided some possible mitigation strategies. The rank represents the order in which NOAA should focus their energy and resources. Using the value hierarchy and cost estimates provided by NOAA, we were able to plot a utility versus cost chart for each design alternative. Alternatives 1 and 2 have almost the same utility, however, alternative 2 costs more by a couple $100,000. Alternative 3 yields the best results, but is far too expensive to implement. Our recommendation is to follow alternative 1 because it has the least cost while still providing good results based on the output. The variability reduction results in saving between 3 to 9 days based on 25% variance reduction. This will save up to 47.4 days of survey time annually, leaving room to conduct another survey or save money in the long run. We would like to thank our sponsor, Sandra Prio, who provided us with a lot of information on behalf of NOAA. We would also like to thank Dr. Lance Sherry, Ms. Paula Lewis, Mr. Juan Montilla for their feedback and support. Thank you for your time.